So yeah, let's get into understanding what is naive Bayes. And naive Bayes is the kind of simplest generative model you can ever think of. And the point is that there is no counterpart for for naive Bayes in the discriminative model world. So you're going to see it immediately. So there is one old classification problem. I mean, the old classic classification problem. And that is that, well, you have an image and you want to classify it. Okay? We all play with that problem in deep learning or machine learning courses. So if you want to solve it, you can use the algorithm which we call it naive Bayes. And it's essentially a generative model. So you use a generative model to solve a discriminative problem. So let me first give you the simplest form of the problem. So it's just the classification problem. I have cat or dog. I'm going to label image of cat by 1, image of dog by 0. And then I assume that my image is a gray image, single channel, k by k pixels. Okay? So very simple problem. I get this k by k image. I want to find out what is the label of that guy, right? Now, I'm going to go and collect a bunch of data points. So I'm going to collect a bunch of images. So they are k by k single channel images. And the labels are either cat or dog. So this is my data set. I assume I have n data points. And essentially, I want to just learn a classifier for this problem. So this is the classical problem. The conventional solution for this one is to just do discriminative learning, right? So what you do, you essentially assume one discriminative model, one conditional distribution, using softmax or sigmoid. And then at the end of the day, you just train the weights of that model using your data set, right? So in old days, when people had no enough computation power, they were always looking for simplest possible algorithm, right? And what is the simplest possible model that you can think for this discriminative task? You want to do classification, a binary classification, and you want to think about the simplest possible model. What is that? Support vector machine is actually a bit advanced, like before that. Sorry? Not tree, no, just a model, sorry? Logistic regression, right? Linear, the simplest one. Think about the simplest one, right? So what is the simplest one? Just do logistic regression. Simplest possible thing when people had no computation. So the idea is that you just put a linear transform here. So you look at your image. For every pixel, you have a weight. You multiply the weights with the pixels. You sum them up. It's a real number coming out of your linear transform. Then you pass it through a sigmoid. It's going to give you a probability. You compute the cross entropy. You minimize it. This is going to give you the classifier, right? So, but the question was at that point of time, can we go even simpler? And then you might say, what are you talking about? This is the linear model. This is the simplest model, right? But actually, there is always a simpler version to a linear model, and that is the tabular model. And what is a tabular model? I simply mean, when I talk about the tabular model, I mean that I don't put any parameter here. I just look at my data set and try to compute the frequencies, and out of that, I compute the probability distribution. Okay? So there is no model involved here. Nothing. It's just a table. You make a table based on what you have seen. You just try to compute the probabilities, right? Approximate them. So for instance, if I want to know what is the probability of my label being 1, I'm going to go over my data set. I see how many images are labeled by 1. So this is the nominator. I put the number of samples I have in denominator. This is going to be the approximation of the probability of label 1 happening, right? So this is tabular approach. This is the simplest thing you can think of if you want to do approximate a distribution, right? So you don't need to have a model or anything. Now, obviously, if you want to try this, it's not going to work for a discriminative learning problem that we have. And do you know why? Do you have any idea why I cannot use this tabular approach? Doesn't seem to be that obvious, right? This is why I asked this here. How is it that obvious, right? But you just write down the estimation that you need to do, and you see why you cannot do it. Let's do it together. for instance, say I want to approximate what is the chance of label 1 given that I have seen image X. How can I approximate this guy? What is the expression for this one? I would go inside my data set, look at every single image that I have, which is X, right? I put that number in denominator, and then among them I see how many of them have been labeled by 1. This is the denominator. Then this is going to be the distribution, right? Everybody's clear? Everybody's clear or not? If you're not clear, I can explain it again because this is important to understand. Yeah? So say I want to know. Say this is my data set. This is my data set, and then I have here x1 and label 1, x2 and label 1, again x1 and label 0, and then x3 and label 1. Okay, say this is my data set. Okay, now what I want to compute the probability of, this is the label. Okay, I want to see what is the probability of y being 1 given that I am seeing x equal by x1. How can I compute it? Can you compute this probability, this empirical probability based on this expression here? Sorry, this data set here? How can I do it? Okay, I assume given that I am seeing x1. How many of these guys have x1? 2. This guy and this one, right? So what is the total number of samples which are x1? 2, right? x1, x1, right? So in 2 of the samples, x1 is happening. Now, how many of them has label 1? 1, right? Then I'm going to say, okay, I have 2 samples with image x1 in it, and then one of them is labeled as 1, so the probability is 1/2, right? Everybody's clear? So this is the way that you can approximate this conditional distribution, right? Because it says what is the chance of label being 1 given that image is x1, right? So when you want to make it given that x is x1, then you need to go and only look at x1s, right? Everybody's clear? If it's not clear, I can explain it again because it's important. If you don't get it, then you don't get what is naive Bayes. You got the idea? How you can approximate this conditional distribution? So you need to just look at those guys which are in the condition. So x1 is happening here. And then we have 2 of that. And then I want to compute the probability of y being 1 in that case. So I have 2 of them. Only one of them has label 1. And then 1 goes here. Now let me just do one else that I make sure that you understood. So say I want to just compute the probability of label being 1 given that my image is x2. What would it be? 1. Why? Because I have only one image with label x2 in it, exactly. So this is 1 here, and then that guy is labeled as 1, so it's going to be 1 by 1, it's 1, right? So everybody got the idea how I am doing the approximation, right? Okay, now if I want to just compute the probability of label being 1 given the image that I'm seeing, okay, I need to go inside my data set and find all of the samples of exact image that I'm seeing, and then I see how many of them are labeled 1, right? But typically when you are doing classification, have you seen that image before? No. Does it exist inside your data set? No. That image is not inside your data set. If it was inside your data set, you wouldn't classify it, right? Everybody's clear? So you don't have any sample usually, or maybe you have just one out of the chance. You don't have either any or maybe just a few samples which are exactly the image that you are classifying, right? So this means that when you want to do this approximation, both numerator and denominator are going to be 0, and then you cannot do it, right? Forget about it. This is impossible, right? So this is why you start by a linear model, because you cannot do this approximation. Tabular is not going to work. The only way that you can do it is to just think of a parameterized model, which is just reducing the complexity by assuming some structure, right? Now, the point is that even though this discriminative learning by a tabular model is not possible, if you think about the generative case, you might be able to solve it. Okay? So the generative case might be possible to be solved by the tabular approach. So how can I do it? Let's look at this one. So if I want to just learn a generative model, I need to approximate this distribution, right? I need to approximate the distribution of y, the distribution of the label, and the distribution of x given y, right? Clear? Now, can I approximate distribution of y? That is not hard in my problem, right? Because probably if I want to know what is p of y being 1, I need to just look at all samples and see how many of them are 1, right? Definitely I have those samples inside my data set, right? For 0 is the same thing, right? So in this case, since I have only 2 labels and I have a very large data set, definitely I have enough samples that give me what is the probability of y being 0, y being 1, right? I can simply approximate it. Everybody's cool? Okay. Next thing, what do I need? I need to approximate this green conditional distribution, p of x given y, which we define it to be the class generative model, right? So I want to approximate this guy based on my data set. So I start to write it down. Can you tell me how should I write it down before I show you the expression? So it's going to be a fraction, right? What is the denominator? Number of samples that have label y, right? What is nominator? Number of samples that have label y and image x, right? So this is going to be the expression. So you're going to look into your data set D. You see how many of them are x and y together. So exactly the x that you are looking for, given exactly the label that you are trying to find out the chance, divided by the number of samples that you have label y, right? So if I think of y being 1, I'm going to go and take all samples with label 1, and I see how many of them are exactly x, right? Everybody's clear? Now, in this expression, forget about nominator, about the denominator. Is it going to be 0 again? No. It's definitely something large, right? If your data set is large, you have enough samples of each label, right? So the denominator is definitely non-zero. But what about the nominator? It's 0, right? Because probably you have not seen the image, right? It's a new image. So you don't have the image. So this is most of the time 0. Most of the time, not time, typo. So, but there is a solution around it, okay? A very naive solution. And the naive solution is that we assume a model for this generative distribution. So we assume a kind of stupid model, but it's still a model, right? For this distribution. We assume that this distribution of x given y is independent for every single pixel inside the image. Okay? If I assume that, then I can find some non-zero value for the denominator. So what do I mean exactly? So let me break it down. This is what we call it naive base. So what you're going to have at the end of the day is this matrix, right? This is your image, k by k, right? So every single of them is a pixel, right? What you assume that given the label, so if you think the label is 1, all of those pixels are independent. Okay? Then you need to know the probability of the first one, second one, till the last one, and then you multiply them. This is giving you the joint distribution. Everybody's clear what I mean by this independent pixels? Would it be the case really in practice? No. This is why we say naive, because it's stupid, but it's still a model, right? It's assumption. I assume it's working like this. This is not the perfect model matching my data, but it's a model. And as long as I assume a model, I can try training it. Yes?
When you make that assumption, wouldn't dimensionality be a problem?
here? No, I'm going to show you. Now you're going to get rid of it, because every pixel is going to be estimated separately, right? It's true that you have not seen the exact image, but probably you have seen lots of images with the first pixel being white, right? Complete white. Yeah? It's the same thing. Yeah? So everybody's clear about this one? So did you get the idea what we assume in the naive Bayes? So in naive Bayes, since I'm not thinking about the discriminative model, I'm thinking about the distribution of the pixels given the label, I can now impose one model on it. And I impose the model to be the most stupid model I can think of, and that is that every single pixel is independent of the others, right? It's not happening in practice. This is not the case. But at the end of the day, it's a model, and I can just train it, right? So I assume that the distribution of this whole matrix of pixels is simply the product of every single of them, right? And then when I do that, then I can train this model on the data that I have using the tabular approach that we did. So one thing that I want to indicate here is that this is just a naive tabular model. This is the most stupid model you can think of, but it's a model, okay? It's not really the case happening inside the data, but when you think about the linear model, it's again not the thing happening in your data, right? You just think that this is the case because this is the easiest model you can handle, right? So it's again the same thing here. Everybody's clear? So by model, I simply mean the simple assumption that I am assuming these guys are independent. Okay. So if I assume this model, then the calculation is going to be easier now. I can readily compute every single of those, conditional distribution for the pixels. Why? Because say, for instance, I want to know what is the probability of the very first pixel to be value 9 given the label that I have. For instance, the label is 1. What do I do if I want to do that? It's going to be again a fraction, right? What is in the denominator? Number of samples, a number of samples in data set with label 1. You have a lot of them, right? What is in the denominator? Exactly. Number of samples you have inside your data set whose label is 1, and the first pixel is value 9, right? So it's true that you might not have seen the exact complete image, but it's likely that you have seen lots of images whose first pixel is 9, right? This is possible if you have lots of samples, right? Now, the point here is that your denominator is the number of samples with the label that you have. Nominator is the number of samples with the same label whose first entry is 9, and then it might be another image, not the image that you are trying to classify, whose first pixel is 9, right? And that guy is going to be counted as well, right? Now, you have no more samples, right? And then this nominator is more likely to be something non-zero, right? If you have so many data, if k is very small, and you have so many data samples inside your data set, at the end of the day, you're going to have for all the pixels them to be non-zero, right? So with large data set, then essentially you can have enough samples which have the first pixel being 9, and then because of that, now you're going to get some non-zero value here. So if you have a new sample x, as I said, you might not have seen it before. This is totally new sample, but you might have seen lots of samples inside your data set for every single pixel of it, right? And then you only need those samples to just compute the generative distribution, right? So even though I haven't seen x itself before, but for every single pixel of it, xij, I might have seen lots of samples whose xij is exactly the same value with label 0, and whose xij is the same value with label 1, right? So it means that I can go ahead for all the pixels inside my data set, and then I just compute all of these marginal distributions, right? Everybody's clear? So you got what we are doing in naive Bayes? So naive Bayes, instead of thinking discriminative, you just write it down in generative form, and then you first compute the label distribution. That is simple. For the pixel distributions, what you're doing, you assume that they are independent. And that is going to be computationally feasible to solve it. Yes?
But if you have a certain pixel that is 0 in all the images,
yes.
Does that make the whole thing?
Yes, yeah, it's going to be again 0. Yeah, this is a problem. So it's not a strong model. But if you think like the example we had, the 5 by 5, 0 and 1, there, I mean, your space is quite small. Like for every pixel is either 0 or 1, and then you always go to compute. Yeah. Questions? No question? OK, great. So that being said, now if I computed this one, so since I can compute for every pixel, I multiply them. I'm going to get the generative distribution for every single, for my image, for, given every single label. And then I can just put it in the Bayes rule, right? So if I want to know what is the chance of one particular label given this image I'm seeing, then in the denominator, I'm going to take this approximation that I have, multiply it with the approximation of the prior. In denominator, I take the same thing for both labels, multiply with the prior of the label, sum them up, right? Then this is going to be the probability of every single label that you, I mean label 1 and 0, given your image, right? And then you're going to take the label which has higher probability, right? If you want to classify. Everybody's clear how naive Bayes works? So this was the idea of naive Bayes. So moral of the story, when you use generative model, since you are able, in this case, since you are able to give a very dummy model for your generative distribution, you're able to use even simpler model as compared to linear model, whereas you could not do it in the discriminative formulation of the problem, right? Because there was no way that you can define the discriminative model in this tabular form, right? So it's somehow making the impossible possible, right? Not really, but it just gives a dummy. It enables you to use a naive model, right? So it's pretty much impossible to just model tabular discriminative learning, but here with generative model, now you can find a tabular model, right? And this is not a strong model, definitely. It has no parameter, essentially. You're just approximating all the distributions, but it's still working, okay? Now, if you wonder whether anyone has used it, actually, many people have used it before. I mean, nowadays, nobody does naive Bayes, but at some point for like language models even, people used to just use a bit of advanced version of naive Bayes, okay? So now, let me check. OK, we have time. Great. So let me just give you one concrete example so you see all the calculations once. So it's going to make it clear for you, all of the story I told you. And then we're going to wrap up everything for this chapter. So let's say that I have that example, that problem that I told you, so the classification problem. Now, to just keep everything super simple, I just assume that I have 2 pixels. OK, it's not 2 by 2 even, is 2 by 1, okay? So just 2 pixels. One of the pixels is x1, which could be A or B. The other one is x2, which is either euro or dollar sign, okay? And I just put it that way to reduce the possibility of confusion in the calculations, okay? So now what is happening here is that I have these 2 pixels, and then I go ahead and collect a bunch of samples, okay? So for the first sample, for instance, the first pixel is A, the second pixel is euro sign, and then the label is 1. For the next one, I have A, euro sign, and then it's again 1, and so on till the last one, right? So I have 2 of these guys here, and for example, B dollar sign 0, and so on going till end. But there is one point here, and the point is that there is no reason that if, for example, euro has been 1, it's always 1, right? Maybe sometimes it's 1, sometimes it's not 1, right? So it's probability distribution. It's not a deterministic problem, right? Now, what I want to do, I want to just classify this sample A and dollar sign. And what you can see is that A and dollar sign is here labeled by 0, right? but I have taken only a few samples. I don't know. Maybe if I sample more, then I see one other sample, A and $, and it's now 1, right? So I don't know about that. What I want to do, I want to classify this guy. And let's first think discriminative. If I want to do discriminative, here actually I can't do discriminative label modeling tabular because the data space is super small, right? So if I think about that, now I want to compute the probability of label 1, right, given the particular new sample that I'm seeing, right? So what should I do? I should look into my data set. I see how many times this A and $sign has happened. And as you can see, it has happened only once, right? Now, if I want to compute the probability of 1 given this guy, in the denominator, what should I put? The number of those samples I found with label 1. Do I have any? No, right? So in denominator, I want to see how many times X, this A and $sign, has happened with label 1. And essentially, when you look at it, you see it never happens. So the probability is 0. Probability of the other one is 1, right? Probability of this label being 0 is now 1, right? And it makes sense because simply, is there any issue? Sorry. It makes sense because essentially what you're doing in this discriminative learning, you look at your data set and you see you have only seen it before with label 0. So you're going to say, OK, the label is 0. That's it, right? Now, let's do generative form. One thing that you can pay attention here is that your model is not reliable because you are basically concluding your inference based on one single sample, right? So you had only one sample, $, in your data set, and your whole conclusion, your whole inference is based on that one, ignoring all the other samples inside your data set, right? OK. Now, let's do it generative. If I want to use naive Bayes, what I need to do, I need to just compute P of X given Y, right? I first go for that one. And I assume that X given Y can be decomposed in the independent form, right? So it's going to be P of X1 given Y times P of X2 given Y, right? This means that I first need to compute the probability of A happening, X1 here, as you can see, given that the label is 1. Now, if I want to compute it, what should I do? I go inside my data set, I look at all samples with label 1, and I see how many of them has first entry inside or entry X1 to be A, right? So how many of them are A? 2, right? So you're going to put here 2 because 2 of them are A, the remaining are B, right? So this means that P of A given A is approximated as 0.4, right? Clear? OK. What about A given 0? What is the probability of A being 0? So again, I'm going to look at all samples with label 0. I'm going to again count the number of them with X1 being A, which is 2 of them, right? And then it's going to be again 0.4, right? So P of A being given 0 is 0.4. P of A being given Y, again, 0.4, right? Now, next thing that I should do, what is it? P of X2 given Y, right? So I need to see what is the chance of $sign happening given label 1, given label 0, right? So I'm going to go for it. So the chance of $sign happening given label 1. So I'm going to look at all label 1s. And then I see how many of them has $sign at the second entry. It's only one of them. So I'm going to put 1 over 5. It's going to be 0.2, right? Same thing going to happen when I change the label. So, OK. So I already have P of A given 1 and P of $sign given 1. So I'm going to multiply them. And then this is going to be P of X, which is X1, X2 given Y, 1, right? Because I assume they are independent, right? So this one we computed was 0.4. This is now 0.2. So it's going to be 0.08, right? This is P of A and $sign happening given assuming that you have label 1, right? Now you can go for label 0. Again, for label 0, you have 5 samples with label 0. Then you see that 3 of them have, at the second entry, $sign. So it's going to be 3 by 5, 0.6, right? and then the probability of x being, given 0 is going to be this one, which is 0.6, times p of a given 0, which we compute as 0.4, so it's going to be 0.24, right? So now I have computed both generative distributions, right? What else do I need? P of y, right? The prior distribution on y. That is quite easy. What would it be? It's going to be half-half, right? Because I'm going to look at this data set. I see half of the samples are labeled 1, 5 of them. Half of them are labeled 0. So half-half is the probability of the prior, right? OK, I have prior. I have generative distribution. So I can compute the posterior distribution, right? So if I want to know what is the chance of 1, given that I have seen x, then essentially I put it in the Bayes rule. And then you're going to end up with 0.25, which initially we computed it to be 0, right? And the other probability is going to be 0.75. Now, what is happening here is that you're essentially getting access, or you are using, based on this naive Bayes approach, you're using all the samples that you have, right? And then all these samples that you have are telling you different things as compared to the single sample you initially thought of, right? Because, for instance, when you are looking here, you see that, OK, when I have $sign in the second one, I am getting higher chance of being labeled 0, right? Or, sorry, the other way around. When the label is 0, I am having a higher chance of seeing a $sign. And this says that maybe there is more correlation between $sign and the label rather than simply A and $sign together, right? So it's using all the samples to do invariance, right? But the point is that you are just assuming this independent distribution, right? Which is a model you assume, right? So if you want to think about it, it's like, have you been in this situation like you ask someone does something for you and that person is not doing, like you write me an email and I'm not responding, right? And then you start to think what the guy is doing, right? And then you would say, OK, maybe the guy is trying to sort things out and then respond to me, right? Maybe the guy has forgotten. You're going to make a model in your mind, right? The model is that I am a like normal person, right? And then I should be like super busy, missing things, or I am waiting for something else to respond. This is the model you make, and based on that, you start to compute probabilities in your mind, and then you decide whether I should write him again or I leave him alone, right? This is the way, right? Maybe your model is wrong, right? I'm a crazy person, so I'm not normal. None of the things you thought is correct. Your analysis is wrong, right? But if your analysis, if your background is correct, then this is going to work, right? Because you are using now all the data, right? Yes?
I don't know if this is the right comparison, but like how we had diagram where we were only comparing with one particular entity for coming up with the result.
The bigram model, I mean the language model you were saying?
And here we have, then we had a model in which we had more context. So similarly, the two examples you've shown, like one has.
Yeah, I mean, if you're thinking only about bigram, that is not hard. Because in your text, probably for every single token and the next token, you're going to see lots of this, right, happening. So that is not a very hard thing. And this is actually like naive Bayes was always used by bigram modeling of the language. Right? But it's a bit more trick into that. So this is the most simple way form of naive Bayes. We usually get rid of some singularities in that one as well, which I'm not explaining here because this is not really practical anymore. Yes?
Can I reduce the terminology of discriminative learning and generative learning to frequentist viewpoint and a Bayesian viewpoint in probability?
You can think of it that way. But the point is that both the, frequency-based look is also still here, right? Yeah, because I am computing everything based on frequency. But your conclusion is right, because what I do assume is that the other samples, which are not the samples I'm looking for, are still talking to me about the decision I'm going to make, Whereas in the discriminative approach, I'm thinking they have nothing to do with that. Yeah.
Yeah, because like Bayesian, what's good about it is that it can deal with like real scenarios.
Exactly.
But
Exactly.
frequentist viewpoint,
Yeah,
it's
yeah.
like the sunrise.
Yes. Exactly. Exactly.
Like doesn't really happen like if it's
Yes, that's totally right. The point is that you cannot ever claim that which one is a good one, right? So nowadays everybody's happy with Bayesian, so good for us, but maybe at some point it's not the case. There is no concrete, I mean, you cannot prove anything about that, right? It's a kind of belief, but yeah, if we feel that, yeah, if anything is impacting the other things, right? So all of these data samples should talk about what we are going to do. But your conclusion is correct, yes. So everybody's clear about naive Bayes? Any question? No question? Great. So moral of the story, here you are using more samples. Essentially, we are using all the samples that you have. And because of that, you are getting it sounds like a more reliable if your prior assumption of independent pixels is somehow meaningful. Okay? So now, as I told you, this idea is not, even though the name is naive, it's not that naive. So at some point of time, people were using it. And there is one famous paper which is worth mentioning. So this is the paper published in 2001 in NeurIPS. And do you know the authors? Do you know them? Yeah, they are quite famous now, right? So at that point of time, the first author was a PhD student. So these are the famous guys writing this one. So Andrew is the one, I mean, everybody knows him, right? And then Michael Jordan, I mean, if it's not the Michael Jordan who plays basketball. Yeah, he's a very famous computer scientist. And the most famous thing about him is the Jordan network, which you have as one of the most primary recurrent neural networks, right? So this is named after him. So yeah, they wrote this paper at that point of time. And the thing was that it's like, if you want to think about the most simple way of thinking generative or discriminative about a problem, then generative is naive Bayesian. Discriminative is the logistic regression, right? Linear model. And then let us compare these two, see which one is outperforming the other. Is it the case that always generative is better than discriminative, or always discriminative is better than the generative? So what they did, I mean, they did lots of analysis, but the whole story can be shown in such a figure. So they were looking into the error that they would get at the end by the model that they have trained in terms of the data size, number of samples that they have. Okay? And what they could see was that this naive Bayes, it has a kind of asymptotic limit, right? So when you use naive Bayes, your error cannot go below something. But it's going to quickly get there. Like if you have after you have a bit of data, more data, then you're going to get to the limit that you can get, right? But the other one, the discriminative model, logistic regression, that one is actually going, I mean, the limit for it is going to be better. Like it's lower as compared to the naive Bayes. It makes sense because, I mean, the independency is quite strong assumption, right? But the point is that this is going to converge there quite slow. So moral of the story was that if you have just a few data samples, it's better that you stick to naive Bayes. Because as we said, like this generative model is giving you the upper hand, right? But when you have enough samples, then a model like logistic regression, since it has parameters, it starts to capture better model of the data, and then it's going to outperform that one, right? So this difference here is essentially because naive Bayes is essentially the most basic model you can think of, whereas the logistic regression has a bunch of parameters, right? So those parameters at some point are going to beat your naive Bayes approach, but you need to have enough data. So if you don't have enough data, it's better to stick to naive Bayes. Questions? No question. Great. So if you got no question, then deep generative models are the deep version of the naive Bayes. Okay? So even though it sounds funny, but that's really the case. Okay? So what you do in in any generative model, you always think that, okay, I have an approximation of the prior, I have an approximation of the class generative distribution, and then if I want to generate a new sample, I just sample the prior, so I randomly sample, oh, it's a cat. Then I go to my class generative distribution and I sample a cat image, right? And then it's going to be a cat image. Of course, if I go ahead and use naive Bayes to do it, this is not going to work, because in that case, I mean, data is super complicated. Naive Bayes is pretty much nothing, so it's not going to work. But this is not because I'm doing anything wrong in terms of a statistical modeling. The issue is that my model doesn't have enough parameters to capture the thing that I want. The model is too simple, right? But the whole thing is the same, right? So if I have more parameters, then I don't need to just work tabular, and then the model is going to get stronger. So at the end of the day, we are going to consider like a super complicated network here. And this network is essentially doing the job that the naive Bayes assumption was doing for us, right? So instead of thinking independent pixels, you think that that distribution is given by a super complicated neural network, right? And then again, you use your samples, use maximum likelihood to train it, and then that's going to give you the generative model. So that is a generative model. As I said, most of you have seen it before without knowing it. And like it's nothing very complicated in sense of statistical terms, but when it comes to computation, I mean, of course, it's going to be super deep. Now that we have it, so we're over with the first part of the course, which was I wanted to start from language models, just gradually push you from the computational way of thinking towards the statistical way of thinking. So I have the feeling you do understand now what I'm going to say in the next chapters. So a quick overview of what we are going to do in the next chapters. We are going to look at two general approaches for generative modeling. The first one is that we are going to just learn the distribution explicitly, meaning that I am going to get one neural network here, and then this neural network is going to take the samples inside the data set and try to just train such that the distribution described by that neural network is approximating the data distribution. How can I do it? I just use maximum likelihood. I have no other way, because I don't know what is the true distribution of the data, right? I mean, we're going to see that even if we knew that, it's no problem, because at the end of the day, maximum likelihood is essentially the same as minimizing the KL divergence between our model and the true data model. But the point here is that maximum likelihood is the same thing we talked today about, and then the only thing I do, I just put one complicated neural network here. Once I train this neural network, training is over. Now if I want a new data point, what should I do? Sample from this one, right? So I'm going to get this model and take a sample from it. And the question is, how can I sample from this? Sometimes it's easy, right? If, for example, I want to generate a token, like what we did in language models, it's a multinomial distribution, right? And it's easy to sample.